Welcome to this explainer. If you've ever stood underneath one of those massive, towering, high-voltage transmission lines and listened to that intense, buzzing hum of electricity, you kind of have to wonder, right? How on earth do we actually control and monitor all of that raw energy? Well, today we're pulling back the curtain on the completely invisible infrastructure that literally makes modern life possible. We're looking at the unsung hero of our power grid, the potential transformer, or PT for short. It's the grid's silent guardian. And honestly, by the time we wrap up here, you're going to see why it is just an absolute marvel of electrical engineering. So let's jump right into the massive problem at hand. Think about it. How do we safely measure the terrifyingly high levels of energy coursing through those overhead lines without, instantly melting our equipment, or worse, ourselves? Our modern grid absolutely requires precise monitoring to balance loads, protect against faults, and keep the power steady. But standard measurement tools, they just aren't built to handle raw, unmitigated grid power. I mean, if you hooked up a standard commercial meter directly to a transmission line, it would literally vaporize in a fraction of a second. So how do we get around this? Which brings us to Section 1, Taming the Voltage Beast. To really get how we solve this, we've got to grasp the sheer scale of the power we're dealing with. It explains exactly why our sensitive, highly calibrated equipment absolutely requires a middleman. Think about these voltage levels. We're talking 11,000 volts, 33,000 volts, and even up to 132,000 volts. These transmission lines are speaking a language of pure roaring power. It's a screaming, high-voltage language that is just way too chaotic and dangerous for standard relays and meters to even comprehend, let alone survive. If a standard meter operates at the volume of a polite conversation, these grid voltages, they're basically a jet engine at takeoff. So we have to take that roaring 132 kilovolt jet engine and somehow turn it into a manageable whisper, specifically a perfectly scaled down whisper of exactly 110 volts. By forcing that extreme high voltage to essentially speak softly, our sensitive electronics can safely listen to what the grid is doing. They can measure it accurately and protect the whole system without getting completely destroyed in the process. And enter our hero, the potential transformer. This is a highly specialized instrument transformer used explicitly for stepping down that extreme high voltage to a safe standard level, typically that 110-volt whisper we just talked about, for measurement and protection. It is the ultimate translator. It stands squarely between the raw, untamed beast of grid power and the highly intelligent, sensitive brain of our modern monitoring systems. Moving on to Section 2, Anatomy of a Translator.
So how does it actually pull off this translation without being blown to pieces itself? Well, a potential transformer isn't just some random hunk of metal. It's an absolute masterclass in precision engineering, built from the inside out with 4 core components. First up, the core. This is made of high-grade silicon steel laminations. And why laminations, you might ask? Because they reduce what engineers call eddy current losses. Basically, we want the energy transferring efficiently across the device rather than just turning into useless, damaging heat. Next is the primary winding, which hooks up directly to that terrifying high-voltage line. Then we have the secondary winding, safely connecting to your everyday voltmeters or protective relays. And finally, the unsung hero within the hero, the insulation. Because PTs deal with massive voltages, the windings are completely immersed in oil or fully encapsulated in tough resin to prevent catastrophic sparks and short circuits.
Now, consider the stark physical contrast in the design of the windings themselves. It's not just about where they connect, it's about the wire. The primary winding, living out there on the dangerous high-voltage side, features a huge number of turns made of incredibly thin wire. On the exact opposite side of the spectrum, the low-voltage secondary winding uses a comparatively tiny number of turns. Keep this mental image of the mismatched coils in your head, because it is the absolute secret to how the whole operation works.
Let's look at Section 3, the invisible hand.
Okay, this brings us to the fascinating physics of the device. This is where we learn how the PT actually translates all that massive power without the two sides ever making direct electrical contact. Let's break this down step by step. The whole thing operates on a physical principle called mutual induction. Step 1. Alternating current flows violently through that primary winding we just looked at. Step 2. As that current flows, it generates a constantly changing, completely invisible magnetic field inside that silicon steel core. And step 3, that magnetic field then expands outward and literally cuts directly through the completely separate secondary winding. The very moment that magnetic field hits the secondary winding, it naturally induces a brand new voltage right there. No physical wires connect the high voltage to the low voltage. The energy just leaps across the gap purely via the awe-inspiring, invisible hand of magnetism. How cool is that?
And the real magic here? The secret lies in a beautifully elegant mathematical equation, the turns ratio formula. V1 divided by V2 equals N1 divided by N2. So in this equation, V represents the voltage on the primary and secondary sides, and N represents the exact number of wire turns we highlighted earlier in those two coils.
Because the number of turns in the primary winding, our N1, is mathematically so much larger than the turns in the secondary winding, N2, the incredibly high voltage is stepped down in exact, perfect proportion. It's a flawless mechanical ratio. And this perfect mathematical proportionality is incredible. It allows grid operators to know exactly, precisely what is happening on a massive 132,000-volt high-tension line just by casually looking at a standard, utterly safe 110-volt dial sitting on a desk.
That takes us to Section 4, choosing the right tool. Now, of course, the power grid is a vast, diverse ecosystem spanning thousands of miles across wildly different terrains and facilities. So engineers don't just use a single type of transformer for everything. First, we have to deal with the physical environment. Indoor PTs are compact, elegant, and usually use a dry resin cast design, since they sit safe and protected inside a substation building. But outdoor PTs, man, they are the rugged survivalists of the grid. They are heavily oil-filled and built inside these robust enclosures designed to survive decades of punishing rain, blistering sun, and corrosive dust.
But what about when we're dealing with truly monstrous voltages? Well, a conventional electromagnetic PT uses standard wire windings and a magnetic core, right? And they are simple and reliable for anything up to 33 kV, or maybe even 66 kV. But step into the big leagues, we're talking voltages above 132 kV, and a standard PT would require so much heavy, incredibly expensive insulation to keep from exploding that it would literally be the size of a 2-story house. Obviously, that is entirely impractical. So engineers invented the CVT, or capacitive voltage transformer. Instead of just relying on a magnetic core, it uses a string of capacitors to drastically drop the voltage before it even reaches the transformer section. It completely solves the massive size and expense problem, making the unit much leaner and cheaper. And here's a mind-blowing bonus. Those CVTs can actually carry high-frequency communication signals right over the power lines, which allows substations to talk to each other without needing any separate telephone wires. That's just brilliant.
Which leads us to Section 5, the golden safety rule. We've talked a lot about the magic of the physics and the brilliant engineering, but working with this equipment is inherently dangerous if you don't know the rules. So we really must pause for a very serious, practical warning: safety first. You must never, ever short-circuit the secondary of a potential transformer. Now, in the world of electrical engineering, you have current transformers, where the secondary must never be left open. Well, the potential transformer is the exact opposite. If you short-circuit a PT's secondary, the device will desperately try to maintain the voltage by drawing an absolutely massive, overwhelming flow of current. The result? It'll immediately blow safety fuses, permanently fry those delicate windings, and completely destroy an incredible piece of equipment. Basically, respect the physics, and the physics will work for you. The potential transformer really is the ultimate invisible bridge between the raw, dangerous power of nature and the smart, safe monitoring systems of human engineering. I mean, without it, we'd be completely flying blind. We wouldn't be able to run modern smart grids, build safe substations, or keep reliable power flowing to our hospitals and homes. But as we move rapidly toward an era of decentralized, renewable energy, with millions of solar panels and wind turbines feeding fluctuating power into a vastly more complex grid, how are these silent guardians going to need to evolve? If this is how we tame the beast today, what kind of incredible, invisible technology will we need to invent for the grid of tomorrow? Something to think about. Thanks so much for joining me on this explainer, and I'll catch you next time.